from part 1 of the video on calculating the accuracy and tolerance on a nonlinear scale of the Simpson 260 VOM, we came up with a few known items that are going to help us calculate the tolerance of resistance readings on that nonlinear resistive scale. So some of the known items from the last video for that Simpson 260 on the R times 1 range is that we know that the open circuit voltage is 1.5 volts. We know that the short circuit current is 1.25 milliamps. We know that the meter's internal resistance is 12 ohms, and we calculated how much current it takes to move the meter 2.5 degrees of arc, which is 3.125 milliamps. So we derived two equations that we're going to need to calculate accuracy and tolerance. Equation number 1 is I is equal to 1.5 volts divided by the 12 ohms plus R. And equation number 2 is R is equal to 1.5 volts divided by the current and then minus the 12 ohms. So you can see that all we're doing here is we have, let me change the color of the pen here, is that we have our voltage, which is the open circuit voltage. We have the internal resistance, which we're going to add to the resistance that we're measuring. Here again we have open circuit voltage. Here again we have the internal resistance. This is going to be the amount of current that we calculated from equation number 1. And that'll give us our R values. So let's do an example. The example that Thomas Morgan used in the article was 10 ohms. So let's use 10 ohms. So at 10 ohms, we can calculate the current using equation 1. So we have I is going to equal 1.5 volts over the 12 ohms of internal resistance plus the 10 ohms that we're going to measure, so that we get 1.5 volts over 22 ohms. So we get a current of 0.182 milliamps. When you press too hard on the pen, it brings up the palette. So at 10 ohms, we have 68.182 milliamps. Now I could calculate my high and my low current tolerance. I already know that 2.5 degrees of arc is equal to 3.125 milliamps. So my high current, or my high tolerance, will be 68.182 milliamps plus 3.125 milliamps. And that's going to then equal 71.307 milliamps. And I can calculate the low current as 68.182 milliamps minus 3.125 milliamps, and that's going to equal 65.057 milliamps. So now I have my currents for the tolerance around 10 ohms. So when I look at the 10 ohms is going to be producing a current flow of 68.182 milliamps plus or minus 2.5 degrees of arc says that plus 2.5 degrees of arc says that I'm going to have 7.1307 milliamps, and minus 2.5 degrees of arc says I'm going to have 65.057 milliamps. So now let's calculate the resistance tolerance for the 10 ohms. So for the 10 ohms, so for the high resistance, so for the high R, I'm going to now use equation number 2, as I want to calculate for R. So I'm going to have 1.5 volts divided by the current. Now, if you think about current for high resistance and low resistance, what happens? The higher the resistance, the lower the current. So I'm going to use, in this case, for the high resistance, the lower current value. And the calculation that we did for low current was 65.057 milliamps. And then, don't forget, we have to subtract the 12 ohms from that. That's what the equation tells us over here. So when we do the high R calculation, we come up with a high R of 11.005, come on, 0.057 ohms. Now I can do the same thing for the low R. So for the low R, it's going to be 1.5 volts, but now I'm going to use the higher current, which is 71.307 milliamps minus the 12 ohms, and my low R is going to now be equal to 9.036 ohms. So for 10 ohms, the reading can be anywhere between 9.036 ohms to 11.057 ohms, and the meter is still reading in tolerance. I want you to notice that these are not symmetrical. You know, when we did the tolerancing for voltage, the tolerance was symmetrical on either side of the nominal value, but here it is not symmetrical. In fact, if you do the percentage of error, you'll have that this is about 10.6% plus, and this is about minus 9.6%. So it shows you right off the bat that this ohms range is not a linear scale, and this is how we can calculate that tolerance based on percent of arc, simply by using how much current it takes to move that pointer plus or minus 2.5% of the arc that it's traveling. So that said, let's do 2 more. In fact, I want to bring up that meter movement. And if you look at this meter movement, we just did the 10 ohm point, which is right here. So let's do, and that was almost mid-scale. Let's do 2 more. Let's do one measuring 2 ohms, which is over here, and another one that's measuring 50 ohms, which is about right, which is not about, but right here. So let's do those calculations. We're going to do them exactly the same way, using the same 2 equations that we used before. So let's do the calculations for 2 ohms. So at 2 ohms, I'm going to use the first equation where I is equal to 1.5 volts over the 12 ohms plus the 2 ohms, which is 1.5 volts divided by 14 ohms. And I get a current that's equal to 107.143 milliamps. So for 2 ohms, the meter's going to have a current flow to it of 107.143 milliamps. And that makes sense because full scale would be 125 milliamps, and I'm approaching full scale, so it looks like it's right. But now let's calculate the high and low currents. So my high current, and my tolerance for that, is going to be 107.143 milliamps plus the current at 2.5 degrees, which is 3.125 milliamps. So my high current is going to be 110.268 milliamps, and my low current is going to be 107.143 milliamps minus the current at 2.5 degrees, which is 3.125 milliamps, and I'm going to get a low current that is equal to 103.993 milliamps. So now I have the currents. That's my current swing. That means I can now use equation number 2, and with equation number 2 I can calculate the resistance tolerance. So my high R is going to equal 1.5 volts over, remember it's the high R, high resistance means lower current, so 103.993 milliamps. So my high R in this case is going to be, I'm sorry, and we have to subtract the 12 from it. I almost forgot that. So this is going to be 2.424 ohms, and my low R is going to be 1.5 volts divided by my high current, which is 110.268 milliamps. Remember, lower current, or lower resistance, higher current minus the 12 is going to give me 1.603 ohms. And that's the tolerance in the resistance for reading 2 ohms. If I look at that in percentage, it's going to be plus 21.2% and minus 19.8%. Pretty big tolerances, but that's exactly how it comes out. And again, they are not symmetrical. Let's do one more yet, and then I'll let you go. So let's do the one at 50 ohms. So again, we're going to do it exactly the same way. Let's calculate the current. I is equal to 1.5 volts over the 12 ohms plus the 50 ohms. That's going to be 1.5 volts, sorry. 1.5 volts over 62 ohms. And that's going to give us 24.2 milliamps. So now we can calculate the high and low currents. So the high I is going to be 24.2 milliamps plus the 3.125. Remember, that's the 2.5 degrees. And that's going to give us an answer of 27.325 milliamps. And the low current is going to be 24.2 milliamps minus the 3.125 milliamps. And that's going to equal 21.075 milliamps. Now I have the two currents, I can calculate the resistance. So the high R, I'm just going to use equation 2, is going to be 1.5 volts divided by high R, low current, 21.075 milliamps, minus 12, which is then going to give us 59.3369 ohms. And my low R is going to be 1.5 volts, low R, excuse me, higher current, 27.325 milliamps, minus the 12, and we're going to get 42.8948 ohms. So this is the tolerance of the reading at 50 ohms. And at 50 ohms, it's plus 18.67% and minus 14.21%. Again, not symmetrical, nonlinear scale. So that's how you would go through calculating the tolerance on a nonlinear scale. That was tough, okay? I had to look that information up also. So if you're really interested in this and need to do this again, you might want to go through these two videos more than once until you really understand, what's going on. And because I got to tell you, it's all just simple Ohm's law and calculating currents and understanding the relationship between voltage, current, and resistance. So that's it for now, and I'll see you in the next video.